In this final exploration of the symmetry of the cube, I'll showcase a number of compound polyhedral forms derived from various polyhedra related to the cube and constructed following the n-fold-in-half method covered in the first two videos in this series. Refer back, if need be, to the first video in the series for an explanation of how these geometries come about. For those of you who have been following this exploration up to now, no further explanation is necessary, as everything you'll see is made following the same procedure as in the previous videos. As such, I won't drag you through the construction of each and every form. Instead, the focus here is simply to showcase some of the intriguing compound shapes made possible by way of directed rotation about various axes of symmetry. Okay then, let's get started. Through the preceding blah 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 of this video's preface, you've been watching me demonstrate a very interesting property inherent to the first three Platonic solids. The nesting being demonstrated here is just one of many interesting and unusual ways these polyhedra sometimes relate to each other. Starting with a cube, by drawing a line diagonally across each of its 6 faces in such a way, those lines become the edges of the tetrahedron, first of the Platonic solids. Going further, by connecting the midpoints of the edges of the tetrahedron, an arrangement of triangles takes the form of the dual to the cube, our old friend, the octahedron, and we find the octahedron's faces perfectly coinciding with those of the tetrahedron. Doing the same to the edges of the octahedron reveals a coincident Archimedean solid, the cube octahedron. This is the prize I'm after. See that within this perfect nesting of geometries, each one is oriented such that the axes of symmetry of the cube coincide with its own symmetry axes. The fourfold, the threefold, and the twofold. And here are the respective compound forms of the cube octahedron, constructed via the n-fold-in-half method. Next up, let's take a look at the rhombicube octahedron to observe how its symmetry is related to that of the cube. As you can see, the cube's 4 fold axes are functionally identical to that of the rhombicube octahedron, as both deal with orthogonal pairs of square faces. The cube's 3-fold axes of its vertices shoot through the centers of opposite triangle faces of the rhombicube octahedron, which are oblique to its normal. The 2-fold axes of the cube coincide with the oblique square faces of the rhombicube octahedron. And here are the compound forms. From the 4-fold, the 3-fold, and last but not least, the 2-fold. Moments ago, we examined the various compound forms of the cube octahedron. I'd like to finish off this series with a showcase of the compounds derived from the cube octahedron's dual, the lovely rhombic dodecahedron. This polyhedron shares 4-fold symmetry with the cube through its top, bottom, and orthogonal side vertices. The cube's 3-fold symmetry is coincident with the oblique vertices of the rhombic dodecahedron. Finally, the 2-fold axes of symmetry of a cube are centered on opposing faces of the r-dodeca. Here are the compound forms, the 4-fold, the threefold. And the twofold compound 6 rhombic dodecahedron. Wonderful. And with that, this series comes to a close. Thank you for joining me on this little geometric exploration. I hope you had as much fun as I did. Until the next one.